So from a really, really high level, this is basically how you concatenate strings, right? This is how you combine strings together. And we're going to jump over the remix to actually explore this ABI.encode pact and this ABI encoding stuff a little bit more. Now, the section that we're about to go through is definitely advanced, and we're going to be going over some really low level stuff and how Solidity works behind the scenes, how the binary works, and this thing called opcodes, and all this crazy low level, tricky, difficult things to understand. If you want to move past this section, there are timestamps in the GitHub repo to help you move past this. However, I do encourage you to at least try to absorb most of this material. If you don't understand it the first time, that's 100% okay. This is more advanced anyways. For most of your basic projects, you won't really need this information. It's only later on, once you get more advanced, that knowing all this is really going to make you a phenomenal Solidity developer. And when you approach this section, when you approach this sub-lesson on EVM opcodes and coding and calling, just know that if you don't 100% understand it the first time, that is okay. If you want to watch this section a couple times, fantastic. So if you want to jump over to Remix and follow along, let's do it. Now in our contract section, let's go ahead and create a new file. We're going to call it encoding.sol. And remember, all the code that we're going to be going with in here is going to be in this sub-lesson folder of the Hardhat NFT FCC. And all the code we're going to be working with is going to be in this encoding.sol. And then in a little bit, we're going to work on this call anything.sol. So we're in this encoding.sol, and let's just make our basic code here. So we'll say SPDX license identifier MIT pragma solidity caret 0.8.7 like that. We'll do contract encoding, boom, compile or Command S or Control S. Great, things are looking good. Now remember, the whole purpose for this is to first understand what's going on here and more about this ABI.encode packed stuff. So let's first just write a function that shows us wrapping ABI.encode packed with some strings, and wrapping it around a string is going to return a string. So we could do function combine strings or concatenate strings. This will be a public pure since we're not going to be reading any storage. We'll say returns string memory, and we'll say return string ABI.encode packed. Hi mom, comma. Put space in here, miss you, like so. So we need another parenthesis here. Okay, great. Now let's go ahead and deploy this. We'll stay on a JavaScript VM. We'll deploy encoding, encoding.sol. And we'll come down here, we'll click combine strings, and we get that whole string output, hi mom, miss you. So what we're doing here is we're encoding hi mom, miss you together into its bytes form, because ABI.encode packed returns a bytes object, and we are typecasting it by wrapping it in this string thing to be a string. And Solidity says, okay, yeah, bytes to string, that's fine, that totally works. And this ABI.encode packed, one of these globally available methods and units. And actually in Solidity, there's a whole bunch of these. There's this Solidity cheat sheet, and there's going to be a link to this in the GitHub repo as well, that has a whole bunch of operators, and it has a whole bunch of these global variables and methods. You can see if we look in here, we look for ABI.encode packed, we see ABI.encode packed right here. If we scroll down, we'll see some more that we're familiar with as well. Like for example, message.sender, sender of the message, message.value. There's a whole bunch of other globally available methods and variables that we can use when we're coding our stuff. Now, I will say though, in 0.8.12 plus, you can actually do string.concat, string A, comma, string B. If you want to, instead of doing this ABI.encode packed, but I still wanted to show you the ABI.encode packed because it's a great segue into all this ABI stuff that we're about to go over. But let's focus on this encode packed thing. So what is actually going on here? Well, before we dive deeper into this encode packed, let's understand a little bit more about what happens when we send a transaction. So when we compile our code, and again, all these pictures are going to be in the GitHub repo. Remember back to ethers.js, we had those two files. We got a .abi file and a .bin or .binary. Back in our ethers simple storage, when we ran yarn compile, the two main files that we got were this simple storage.abi which was this, this ABI thing that we've become familiar with. And then the simple storage.bin, which is the binary, which is a whole bunch of just numbers and letters and stuff we didn't understand. And you can see that in Remix too. Like if we were to compile this, you go to compilation details, you get a whole bunch of stuff in here, right? You can see the ABI in here, which this is kind of like a different way of viewing that ABI. We also get this bytecode bit, and it's this object that has the same stuff, that has like those random numbers and letters, but this is actually the binary. This is actually what's getting put on the blockchain. It's this binary, it's this low level stuff. Now, when we actually send these contracts to the blockchain, we're sending, like I said, we're sending this binary thing. That's exactly what we're sending to the blockchain. And remember how, again, back in our Ethers project, we saw what is a transaction, right? A transaction has a nonce, it has a gas price, gas limit, to value data. We kind of skimped over the VRS a little bit because that's kind of that mathy component of the transaction signature. But again, back in our Ethers project, we did this as well, right? In our deploy script, ended up sending a transaction ourselves using just Ethers. We passed a nonce, a gas price, gas limit, to value. Data was this massive thing to deploy our contract, and then also the chain ID. We didn't work with the VRS because Ethers does that for us, but there's also this VRS component that we don't bother to look at. When we send a transaction that actually creates a contract, the to is going to be empty. We're not going to send this contract deployment to any address, but the data of this is going to have the contract initialization code and contract bytecode, right? So when we compile it, we get all this code, like how do you initialize the contract, and then what the contract actually looks like. So if you look at any of the contracts that you deployed, for example, I'm going to look at our raffle that we deployed. If you go to the transactions of your contract, we can see create raffle, right? Let's go to that transaction. If we go down and click to see more in Etherscan, we can see this input data thing. And once again, it's got all this random garbled numbers and letters. This is that binary data of the contract initialization code and the contract bytecode, right? What we send in our transaction is this data thing. We send this weird bunch of jarbled nonsense. Now we're going to head back to Remix, and I'm just going to leave this as comments in here. In the encoding.sol and the GitHub repo, there is a ton of comments in here explaining exactly what I'm explaining. So if you want to follow along there, you can as well. But now, in order for the blockchain to understand, okay, what do these numbers and letters even mean? You need a special reader. Ethereum, or the blockchain, needs to be able to read all this stuff. It needs to be able to map all these random numbers and letters to what they actually do. How does Ethereum or Polygon or Avalanche know that all this nonsense is basically telling it to make a contract? You kind of think of it as saying like, take off your coat. The only reason that we as human beings understand what take off your coat means is that we understand English. We're all reading English. For Solidity and for blockchains, instead of English, they read these numbers and letters kind of like words. Just instead of take off your coat, it's like deploy contract, and the contract does X, Y, Z, and all this random stuff. So this bytecode represents the low-level computer instructions to make our contract happen. And all these numbers and letters represent kind of an alphabet, just like how take off your coat is an alphabet. And when you combine them like this, it makes something that to us makes sense. You can kind of think of the alphabet for these as what's called opcodes. If you go to create a new tab, if you go to evm.codes, we'll get to this place where it just has a list of all these instructions. On the left side, you can see this thing called opcode, and then you can see name. So this opcode section is saying, hey, if you see a 00 in this bytecode, that 00 represents this opcode stop, which does what? Which halts execution. If you see a 01, you're going to do some addition stuff. A 02 is multiply. There are all these opcodes that are kind of like the alphabet or the language of this binary stuff, right? And they go all the way down to FF self-destruct. These opcodes also have, and that's what this is reading, right? So if we look at our transaction here, and yours might be a little bit different, 061 says, okay, the first thing we want you to do is the 061 opcode. And if we go to EVM opcodes, we look up for 61, it's saying push to, place 2-byte item on the stack. That's exactly how it's reading this. Any language that can compile down to this opcode stuff, down to this specific set of Ethereum opcodes or EVM opcodes, is what's known as the EVM, the Ethereum Virtual Machine. So being able to read these opcodes is sometimes abstractly called the EVM, the Ethereum Virtual Machine. The EVM basically represents all the instructions a computer must be able to read for it to interact with Ethereum or Ethereum-like applications. And this is why so many blockchains all work with Solidity, because Solidity compiles down to this bytecode here, and Polygon, Avalanche, Arbitrum, Ethereum, they all compile down to the exact same type of binary, and they all have the exact same readers. Now, why are we telling you all this stuff? You might be saying, hey, Patrick, this is cool and all, but it looks like ABI.encode packed, all that does is concatenate strings. ABI.encode packed can do actually way more. And if we look at these global variables, ABI.encode packed is like what, the third one down the list, because it's a non-standard way to encode stuff to this binary stuff that we just talked about. We can actually encode pretty much anything we want to being in this binary format, basically. And let's take a look at encoding something. So let's create a function called encode number. And this will be a public pure function since we're not going to read any state. And we'll say returns a bytes memory. We're going to have this function return a bytes object. We're going to have it return what this number is going to look like, but in binary. So we'll say bytes memory number equals ABI.encode 1, and then return number. So we're going to encode number down to its ABI or its binary format. So I know a lot of the times when we say, oh, what's the ABI? What's the ABI, right? Previously, we say, oh, the ABI is this thing, right? It's all these inputs and outputs. This is kind of the human readable version of the ABI. But again, the ABI is the application binary interface. We want to encode our numbers down to its binary. This ABI.encode is going to be a little different than like the ABI that you see when you're looking at compilation details. This is technically like the ABI. It technically is how to interact with this contract. However, it's not the actual binary version of it. So we're saying, okay, encode this number 1 down to its binary version so that our contracts can interact with it in a way that they understand. So we're just saying, okay, cool, that number 1, let's make you machine readable. And if we go, we compile this and we deploy this, right? Let's delete that old contract. We deploy this. We now have combined strings and encode number. If we click it, we get this big hex thing. This is how the computer is going to understand the number 1. Now we can encode pretty much anything, actually. We could encode a string. So we'll say function encode string. We'll make this a public pure as well. It'll return a bytes memory because we want to give it that binary stuff or that byte stuff. And we'll say bytes memory some string equals ABI.encode some string, and then return some string. Now let's compile that. We'll delete our old contract, deploy that, encode string. We get this big object here. And this is the binary. Now you'll notice something here. There's a ton of zeros, and those zeros take up space, right? That's a lot of space for the computer to take up, even though they're not really doing anything. They're just kind of taking up space. So Solidity also comes with this ABI.encode packed, which performs packed encoding of the given arguments. And you can read more about it in the Solidity docs if you want. And this is called the non-standard packed mode. And it does the same encoding with some stipulations. Types shorter than 32 bytes are concatenated directly without padding or sign extension. Dynamic types are encoded in place and without the length. Array elements are padded but still encoded in place. You can kind of think of encode packed as sort of like a compressor, right? It's the encode function, but it compresses stuff. If we wanted to encode some string, but we wanted to save space and we didn't need the perfect low-level binary of it, we could do function encode string packed, make this a public pure, and have it return a bytes memory. And we could say bytes memory some string equals ABI.encode packed, once again, some string. And so we're doing encode packed instead of encode, and we'll return some string here. We'll compile this and we'll see the difference, right? We'll compile, we'll delete our old one, we'll deploy this. Now we have encode string, which again, that's what encode string is going to give us. And we have encode string packed, which returns us this much smaller bytes object here. So you see the size difference. If we're trying to save gas encode string packed is going to be a way for us to save a lot more gas. Now, ABI.encode packed is actually really similar to something that we've done before, which is typecasting. If we did function encode string bytes, public pure returns bytes memory some string equals bytes some string, return some string. These two are going to look nearly identical, right? So if we compile, we'll delete our old contract, we'll deploy this, encode string bytes, which gives us this, and encode string packed using the ABI.encode packed. They give us the exact same output, whereas encode string still gives us this big piece. So the two of these get the same result, but behind the scenes, they're doing something a little bit different. And I'm not going to go over exactly what that is, but I've left a link inside of the code here if you want to learn more, which is exactly what we're doing in our NFT, right? We're doing ABI.encode packed. We're combining two strings by putting them together. We're encoding them to their bytes implementation, to their packed bytes implementation, and then we're just typecasting them back from bytes to string, and that's how we concatenate them. Now, at this point, you might be thinking, okay, cool, great, Patrick, I'm all set. I understand this. I'm happy to go back to my project. And if you want to do that, absolutely go for it and skip over this section. But some other views might be going, okay, Patrick, this seems pretty cool, but I'm sure this encode packed and this encode function aren't just here to concatenate strings. They probably have some other function. What do they actually do? Well, if that's what you're asking, I'm glad you asked, and I'm glad you're curious because we're going to find out. Now, not only can you encode stuff like strings and numbers and really anything, but you can decode stuff. So I could say function decode string public pure returns string memory some string equals ABI.decode. This is going to take a couple parameters. So if we look in the docs here, ABI.decode, it takes as a first argument the encoded data, and then it takes a tuple. You can kind of think of it as a list, but not quite a list, a set of types to decode this into, and it returns the number of parameters that you gave it. So we might want to say this string memory some string, let's give it as input this encode string function, the result of this encode string function, right? Which again is going to be this big thing. So this is kind of equivalent to sticking this massive thing in here, but we're just not going to stick the massive thing in there because that's really big. So we're going to say, let's decode the result of encode string and let's decode it into a string. Because we need to tell Solidity, hey, we're going to decode this, but it doesn't know what to decode it into. It's like, okay, cool, I can decode this, but like, what do you want me to do with it? And we say, oh, this is a string. So decode it into a string, and then we can do return some string. Now, once again, we deploy that old we delete the last contract, we deploy this new one. So encode string, where is encode string? Encode string returns this massive thing. As a human being, we're like, I can't read that. Computers can read that, but we can't really read that. So we say, okay, let's decode that back into its string form. We hit decode string, and we get back some string. And now we can actually multi-encode and multi-decode, right? We can encode as much stuff as we want. So I can say function multi-encode, public pure, returns bytes memory. We're going to encode a couple things. We'll say bytes memory some string equals ABI.encode some string, comma, it's bigger. So we're going to encode two strings here. We're going to encode some string and it's bigger. So we have two strings we're going to encode, and we'll return some string, even though it's, bytes. And then we can actually multi-decode. So we'll say function multi-decode. This will be a public pure. Returns, we'll say it returns two strings, string memory and string memory. And instead of doing string memory some string equals ABI decode, we'll say string memory some string, comma, string memory, some other string. So we're going to get two returns equals ABI.decode. Let's decode this multi-encode result, which is the doubly encoded strings, into a string and another string. And then we'll return both of these, or some string. There we go. Then we'll return some string and then some other string. I need a semicolon here. So now when we deploy this, let's close this out, deploy this new one, right? We now have this multi-encode, which gives us this even bigger bytes object, right? Because this is 2 strings encoded. And now if we hit multi-decode, take a second, what do you think it's going to put out? Output. Let's go ahead and hit it. Now it's going to give us 2 strings, right? It's going to give these 2 strings, some string, it's bigger. So we can tell Solidity to encode a bunch of stuff, and then we can even decode it by telling it, okay, this big object here, it's 2 strings combined, and then we decode it. Now you can even multi-encode with that encode packed thing, right? We could do function multi-encode packed, public pure returns bytes memory, and then bytes memory sum string equals abi.encode packed sum string, comma, it's bigger, and then return sum string. We could do this, right? But this is going to give us the packed version of these 2 strings. So the decoding actually isn't going to work on this because this is packed encoding. So if we tried to do, I'm going to say this doesn't work. We tried to do function multi-decode packed public pure returns string memory sum string equals abi.decode multi-encode packed, and then in a string, kind of exactly what we did above. To if we do return some string, what do you think is going to happen? Well, let's try it. Delete the old contract, deploy a new one. We'll do multi-decode packed, multi-encode, multi-decode packed, and we actually just get an error. Solidity basically goes, yeah, this looks like it's packed. I don't know how to decode that. But instead, what we can do is we can do function multi-string cast packed, make this a public pure, returns string memory sum string equals string multi-encode packed, return some string. This one will work, right? Because again, this packed encoding is kind of similar to just typecasting. So we'll compile, we'll redeploy, multi-string cast packed. We get some string, it's bigger, right? And we don't have a space here, but we should have put a space in there.